Hi everyone. In this video, we are going to talk about an asynchronous ripple counter. We're going to make a 3-bit ripple counter, which means it will have 3 binary digits and be able to count from 0 through 7. We're going to make these using JK flip-flops. So remember, JK flip-flops have a J and K input. They have Q and Q bar as outputs. They also have a clock input, and we're using a negative edge triggered flip-flop. And this is our clock input. We put the bar on it because it's negative edge triggered. And sometimes these JK flip-flops also have a direct set line, so we could set them directly in a direct reset line. Notice that with the bubbles on them, these lines are active low. So I'm going to tie the set line high to a logic 1, or you would tie it to 5 volts in the lab. And then and not every chip has that automatic set. The direct reset, that is an override line, and I'm just going to tie it here to a signal. And the reason I'm doing that is when I run this circuit, I would like to be able to initially set RD low to reset my circuit, and then I would set RD high for the rest of the time to get it out of the way. Now, or to make sure it's not having an effect and overriding my outputs. So when this reset line is high, it's not affecting the outputs. When the reset line is low, it is overriding the outputs such that Q is 0 and Q bar is 1. For the J and K inputs, I want this flip-flop to be in the toggle state. So J and K would also be tied to a logic 1 or to 5 volts in the lab. And let's look at what this output Q0 would be. So let's color code this. I'll make Q0 purple here and Q0 purple down here. So with both inputs J and K tied to 1, this flip-flop is going to be in the toggle state. Okay, so with J equal to K equal to 1, that's the toggle state. And we know that the output of this flip-flop is going to toggle on the negative edge of the clock. So we had best also put a clock signal there. And remember that the reset line is a direct override, so it's ignoring the clock signal. So we should know that. So here's my clock signal just going up and down and up and down. Okay, and I want to draw my output Q0. So remember, Q0 is just going to toggle on the negative edge of this clock because J and K have been set both high, and that is the toggle condition. So with every negative edge, Q0 is toggling, which means it is going to the opposite state of the one that it is in. Okay? Now, that gives us 1 bit. For our next bit, I'm actually going to do many things the same. So I also want this flip-flop to be toggling. So I am going to tie J and K high, and I realized I just wrote J and K backwards. So let me fix that. We write J at the top and K at the bottom. I have Q and Q bar as outputs. Now I have a reset line which I will tie to the other reset line so that all the outputs get reset together. And I have a direct set line that I will tie high. And now the clock input to this next flip-flop, I'm not going to join it to the other clock. What I'm going to do is join it to Q0, the output of the previous flip-flop. That means that this output Q2 coming, or sorry, Q1, let me erase that. Q1 coming from our next flip-flop here is going to toggle on the falling edge of Q0 because Q0 is the clock to that flip-flop. So Q1 is going to start reset, and then on every falling edge of Q0, it is going to toggle, just like that. Okay, and that gives us a second bit for our counter. Now we said we wanted to build a 3-bit ripple counter, so I'm going to add yet another JK flip-flop to my circuit. And you can see a pattern in how I'm making these connections. I'm going to try the direct reset line to the others. I'm going to set the direct set line. Oops, I drew my bubble in the wrong spot there. My direct set line is going to be tied high. My J and K are going to be tied high. And the clock of this last flip-flop is going to be tied to Q1, the output of the previous flip-flop. Okay, and I'm going to call the output of this last flip-flop Q2, and it will toggle with every falling edge of Q1, which is just these two edges right here. So it's going to start reset like everybody else, then it's going to toggle, and then toggle back. So, and this is Q2. So if we turn our head sideways and we look at Q2 and Q1 as a binary number, this is our most significant bit. This is our least significant bit. And we can see that these numbers are going 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And then you can see all three go back to 0. So when I turn my head sideways and look at these Q outputs, this circuit is counting in binary: 0, 1, 2, 3, 4, 5, 6, and 7. Okay, and there's also something nifty we could do here. And so this counter is counting up. It's counting 0 to 7. If I wanted to take, if I wanted to have this counter count down instead, the only difference I would make is I would use the Q bars as my outputs instead. So just looking for a pen color here. I'm drawing this in orange. So these bottom ones, I would say, use these instead if you want to count down. if you want to count down. Okay, so now I'm going to show you that. I'm just going to scroll my diagram up a little bit. So you can't see the diagram, but I'm taking the Q bar outputs as my outputs for when I want to count down. And actually, let me change my notation here a little bit. Instead of calling them Q's, because I'm taking the two bar outputs, let me call this 2 to the 0, 2 to the 1, and 2 to the 2, representing least significant to most significant bit. So let me draw those outputs here. So 2 to the 0 is, and actually I'll draw it in purple to match Q0. 2 to the 0 is the opposite of Q0, right? Because now I'm taking the output from the Q bar. So where that signal goes up, this one is going to go down and vice versa. So I'm going to get this. Okay. For 2 to the 1, it's the opposite of Q1 because it's taken from the Q bar output. So it is going to be high, then low, then high, then low. And same thing for the 2 to the 2 output. It's going to start off high, then go low, then back high. So if we turn our head and analyze this, if this is most significant bit and this is least significant bit, I've got 1, 1, 1. Actually, let me draw those the right way around. So 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, and then it goes back to 1, 1, 1. So once again, what I have done here is to say use the Q outputs to count up and use the Q bar outputs to count down. Otherwise, the circuits are the same. Okay. Now, the next thing we're going to look at is what if we want this circuit to not count all the way to 7? What if we wanted this circuit to reset? Okay, so I'm going to redraw the circuit quickly, and then we'll do an example of what if we want this circuit to reset. So if I have if it's a 3-bit count, I'm going to have 3 flip-flops. They're negative edge triggered. Inputs J and K, outputs Q and Q bar. I have a direct set line tied high so that it's not being used because it's an active low line. Now I have a reset line that I am going to use. And for now, I will just tie all the resets together. Because I want to do, let's say in this example, an up counter, I'm going to take my outputs as Q0, and I'm taking them from, and actually let me write, oh, that's fine. I'm taking them from the Q output. I'm going to use the Q output of the previous flip-flop to drive the clock of the next. And my first flip-flop just has a regular clock input, okay? And so what I want to happen is, say, like normally, as we just saw above, this circuit would count 0 through 7 in binary. Now, what if I only wanted it to count 0 through, I'll do the example we did in class, 0 through 4. So this would be a mod 5 counter. It's got 5 states, meaning I only want it to count 0 through 4. What we can do is make use of this reset line, okay? And I'm going to rewrite my words over here just to get them out of the way. So this is, we want 0 through 4. That's what we want. And we call this a mod 5 counter arrangement. So I can use the reset line to my advantage. The interesting thing about these counters is when it is counting normally, it's going 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. But we've decided that we want it to only count 0 through 4, and then we want it to reset and go back to the beginning, right? Which means if the output hits 5, we want it to reset. Now, output, because this goes in order, because the counter counts in sequence, this will be the first time that both the 2 to the 2 bit and the 2 to the 0 bit are equal to 1 at the same time. And so what I can do is I can tie to my reset line, and I'm just going to make a little bit more space here on my diagram. I can tie to my reset line a NAND gate, and I'm using a NAND gate so that it gives me a low output when my conditions are true, because I know the reset line itself is active low. And then I am going to tie, actually I'll draw this in a different color so you know that this is our special edition here. So green doesn't show up very much. I'll make it red. So I'm using the NAND gate. It will give me a low output when its inputs are both high. And what I want is this 2 to the 2 and 2 to the 0, because that's the condition for when the output becomes 5. So I'm going to tie one to that output, and the other one, I'm going to jump around my circuit here and tie to this output, right? I've drawn that a little bit messy, but you can see I'm tying to the 2 to the 0 and the 2 to the 2 outputs. So when they both become high, and the first time that happens is when the output hits 5, it is going to force a reset. Then all the outputs will go back to 0, and then it will start counting up again, right? And what you see, what you'll see in the timing diagram, you still have your clock, okay? And you have Q0, so this was clock. You've got Q0 toggling, and you've got Q1 and Q2. Q1 and Q2. So initially they're all 0. If we've put our little made an initial reset, okay. Now this is our state 0, 0, 0. And then we have our next state, which is 0, 0, 1. Then we have our next state, which is 0, 1, 0. And our next state, which is 0, 1, 1. Then Q2 goes high, so we have 1, 0, 0. And then we go to state 5, which is 1, 0, 1. So we have, this is still 1, this is 0. When this one goes high, just for this brief tiny bit of time, we will have 1, 0, 1. Then what happens is we get the 1 and the 1 here on the NAND gate. That causes a 0 here, which forces the reset. So all the outputs are forced to 0. Okay, and then the counting continues, and we have 0, 0, 0, 0, 0, 1, etc. So the key thing to take away from this is we have we've added this NAND gate to reset when we reach a certain condition. That certain condition will appear for the tiny amount of time that it takes for the signal to reset the gates, right? So there's a little bit of a glitch there. You wouldn't see it with your eyes if you noticed in the lab circuit. We didn't see it with our eyes, but if we were measuring the waveforms on an oscilloscope, there's a tiny little glitch here where it takes a minute for the circuit to actually be reset, and then it starts counting over. So this circuit, we say it counts 0 to 4 because we ignore that tiny glitch on the 5 when it resets.